Thanks for having me here. I'm excited to be here to kick things off. I'll be talking today about kind of the beginning of a project that I've been doing with some people at NCAR. So this is the group that I've been working with. It's led by James Doan over at NCAR, and the goal of this project is to understand highly extreme precipitation events or extreme climate events in general. And the reason we want to do this is because we know that highly connected extreme precipitation events can have widespread and severe impacts. So this map here shows the rainfall that fell during Hurricane Harvey in 2017. And you can see the really large spatial extent of this rainfall, and this is over 7 days, so this event was highly connected in both space and time and led to many damages, including tens of fatalities and over $125 billion in losses. So these can be really impactful in these damaging ways. They can also have a different kind of impact. Something we've been interested in this project in looking at is kind of how these connected events, extreme precipitation events, can maybe alleviate drought conditions or end fire seasons. So this is some maps showing the impact that a series of connected atmospheric rivers had over a week in California. So you can see on the left the drought conditions that California was in January 19, 2010. You can see that a lot of California was either in moderate and even severe drought. And after getting a lot of rainfall during over 1 week in January, 1 week later, this helped alleviate a lot of the drought conditions. So the series of atmospheric rivers helped alleviate drought conditions over California. So we want to understand what is the impact of these events and kind of quantifying how they're connected in space and time. So the main research goals of this project, of the big project, is to identify and quantify connected extremes, understand their drivers, and then quantify their impact. And lastly, we're doing all this in order to also try to understand whether there's some sort of subseasonal to seasonal predictability of these connected extremes. And that will help us understand the impacts better. In this specific talk, I'll be talking about the methods that we use to identify these spatio-temporally connected precipitation events. I start to talk about this data set we've created and kind of the characteristics we've been seeing of these connected extremes. And lastly, I'll talk a little bit about how we're using these extreme precipitation events to quantify their impacts. So I'll dive a little bit into kind of what's been done in identifying connected extremes. So this is work that we did a few years ago that I did in my PhD, where we quantified kind of the 1D connectivity of extreme rainfall using geostatistical frameworks. And this allowed us to use station data or point data to quantify kind of the extents of extreme precipitation over space. So by being able to use station data, we could go back in time. We could go over the full 20th century. When you have a gridded data set, you can use image processing tools, or there's different ways to describe these tools, but I'm describing it as binary image processing tools. And this is something that's been done, that we did in a different project, but also has been done more in the weather forecasting field to kind of verify forecasts. So you can see you can go from having a precipitation field to having kind of precipitation objects that you've defined as being connected in space. So this is more of a 2D connectivity that you can then look at different 2D characteristics like the area or the total rainfall of different objects. What we're doing is kind of taking this and extending it into 3D. So we're trying to identify connected extremes in both space and time. And this has been done before. And I also want to um, say that it's actually also being done in a very similar way by a different group at Lamont. And they're actually using this method to quantify the connectivity of marine heat waves. So this isn't that's being done, but this is something we've developed to look at extreme precipitation specifically. So the way that this works is we first create a binary image for each day with extreme grid points equal to 1. So this is just an example series of days. So you're looking kind of like a north to south, east to west, and each grid point here that's in blue is an extreme precipitation, a grid point that is experiencing extreme precipitation. So the first thing that we do is we close gaps between extreme grid points, and this allows us to kind of limit the gaps between objects might be connected together. So kind of overcoming some of the errors you might get with grid point data sets where some objects are separated but are part of the same rainfall event. So we've filled these in gray over here. And then lastly, we just use an image labeling method to find the spatially and temporally connected objects. So those 3 days of rainfall are considered one object because they overlap from day to day. So you can that they overlap from day 1 to day 2 to day 3. So in this little toy example, this is one connected object. For our specific project, we're creating extreme event objects using the ERA 5 dataset. So this is reanalysis data on a 25-kilometer resolution going from 1979 till present. And to define our extreme precipitation grid points, we use the monthly 99th percentile of rain days for each grid point. So each grid point has different 99th percentile for each month, and that's how we define our threshold for extreme rainfall or precipitation. And lastly, we use that image processing framework that I just described to identify objects and quantify their characteristics. So when we do this for the ERA 5 dataset, we get over 32,000 extreme precipitation objects over the US over those 40 years. And for each object, we have a series of characteristics that we define, its location on each given day, its area, its duration, and then any precipitation and impact characteristics that we could think of. So if you're interested in knowing more about the specificities of this data set, I'm happy to talk later, but kind of just wanted to give an overview of what this data set looks like. So I'll dive a little bit into some preliminary analysis that we've done on these data sets, on this specific data set. So here I'm going to be showing some plots for different regions and seasons. So I forgot to include a map here, but basically these are different, quite broad regions over the US. So going from the boreal region in the north, central, desert, east, mountain west, Pacific, and west south. And what I'm showing here is simply just the number of events over those 40 years that we have for each region. So you can see that the number of events differs for each season and region. In the summer, the central region has the most events, and in the winter, the Mountain West has the most events. So this is something we're going to start looking into to understand why different regions and different seasons have a different number of events. Another thing that we've seen is that the area or footprint of the events varies per region and per season. So you can see that, again, the boreal region has the largest events, but there are some seasonal variations where summer footprints are generally smaller than winter ones. And this is something we've seen in previous studies as well, where summer spatial extents are smaller in the summer than they are in the winter. And we can start to try to understand kind of the orientation of these events for seasons in different regions. So here I'm showing the frequency of these events for the Pacific region for the different seasons going from winter to fall. And you can see that in the winter, you have larger events, and you can see that they're kind of oriented in a different way too. So you can see that they're kind of spread out over the Pacific coast here, and they spread out into the Pacific Ocean quite a bit. In the summer, on the other hand, they're centered more around the Pacific Northwest, so Washington and Oregon, and they're not so spread out over the Pacific Ocean as much as they are in the winter. So again, we kind of know this is the longer events here are kind of a feature of atmospheric rivers, but we're going to try to understand these a little bit more. Here I'm showing, we see that there's seasonal variations in the duration of events. So you can see here it's the number of events on the y-axis, and this is kind of a histogram for different duration of events. And you can see that most events are 1 day long. This is a log scale. But there are some long events, and those long events seem to be more frequent in the summer than other months. When we look at specific regions and seasons for these different duration events, we see that in the Pacific region, these long events usually occur in the fall and the winter, but in the southern region, they occur mostly in the summer and the fall. And so we can start to ask, is this because we have atmospheric rivers in the winter and the fall in the Pacific? And in the summer, is this a feature of maybe tropical cyclones? So this is something we're going to start to investigate a little bit more. And lastly, we also kind of try to look at the impact of these extreme precipitation events on fire weather. So here I'm showing just for the Pacific region and the Mountain West, where we do get some large wildfires. And in the summer and the fall, this is usually the fire season. What is the impact of these extreme precipitation events on fire weather? So we look at the footprint of where these extreme precipitation events occurred, and we just look at the difference in a given fire weather index after the event has passed. So you can see that in almost all objects, there's a decrease in fire risk. But you can see that there's different levels of this decrease in fire risk. So I've started to dive into this a little bit, and I still don't understand what the spread is coming from. I thought maybe larger decreases in this fire weather index would maybe stem from more precipitation, but as of now, it does not seem to be the case. There seems to be not much of a relationship there, or maybe something that's opposing my hypothesis in terms of the impact of extreme rainfall on fire weather. So this is something I'm going to dig into a little bit more and try to understand kind of the impact of these precipitation events on something like fire weather. So I will leave my takeaway points here since I went over time, and I am happy to take any questions.